Let me just get my notes where I can see them. Oh, and let's not forget to share the screen because I've done that before. Okay. So, today we are doing, wait for it. There we go. Section 5.7 in the book. And it's just going to be the integrals based on the derivatives we learned last class. So, last class, we learned these derivatives and we went through and proved them using triangles as to why they're true. All right, and Claire, we're just copying down what's on the screen right now. These are our new rules of the day. And Gabe, are you taking notes? Okay. So the notes I have prepared are just practicing the problems. What are these going to look like? Sometimes we'll teach you a couple of tricks, but for the most part, it's just going to be pretty straightforward. And I'm just kind of watching you. I can see some people are finished with the notes, but it looks like others are still taking them. Thanks, EJ. That helps a lot. Yeah, for those of you without your cameras on, if you give me some indication, that does help, because I know a few of your cameras aren't working right now. Thank you, Trisha in Brooklyn. Kaomi, let me chat with you when I have both my hands free. But yes, we can figure that out. All right, wave at me if you're still taking notes. Okay. Okay. All right, so let's use these. Oh, excuse you. And just show you what these could look like. When it comes to derivatives, there are more rules for learning how to take the derivatives. But when it comes to integrals, there's just all these individual, I don't know, there's almost more you have to keep up with, which is why we're just teaching you a set at a time. Many of them still will use what we had in the basic skills test, but then they also use these own rules on top of it. So on a problem like this, we could see if we were to use U substitution, we would say that U equaled the 4 minus x squared. But the problem with that is we'd end up with a term we don't have in the problem. The 2's not such a big deal, but that x is not in the problem. But luckily we have this trick that we can look at it and say, I could use this rule about, I'm going to write it in a different color just so it pops a little bit more. I know that if I take the derivative of a squared minus u squared, oh, but let's see, make sure that that's a u just to match the rules we had before, that this is going to be the arc sine of u over a plus c. And so this is just working in reverse from that derivative rule we learned last time. What we can do here is we can say that our a we can see would be 2, because it's 2 squared, and our u would be x, and whenever you use just x, just leave it as x. Just use the x's instead. So this would give us 2 squared minus x squared, which will put things in this order. So today, with the way I've got my lesson set up, we are going to focus just on, this is the rule, let's just use the rule instead of working our way through and reinventing the rule every time. Okay. Everybody finished with this one? Okay. Let's call that number A, and on to number B. And honestly, I'm going to go ahead and give you number C as well. I want you, and it should be fairly straightforward which rule we're using on each of these. I want you to find what your A value and your U value would be for each of these, and use the rules at the top of the page, the first rules I gave you, to figure out what these integrals would look like. You're gonna behave for me? You want the tray? I should have pointed out, where you have U's, you do have U substitution. So if you need to make any little modifications on your integral, watch for that. Okay, check your work against mine for both those problems. I'll circle back through in a moment. Now, when I was in college, we had a professor who was absolutely incredible, named Dr. Peacher. In fact, we used to call him the Peachinator. We made a peach and put eyes on it and made him a superhero because we thought he was so cool. But one of his trademarks, besides getting chalk all over his face, because we had chalkboards instead of whiteboards, and he'd always touch his face and he'd get chalk on his face. His other big trademark is he would go through and he'd do the math in the problem, because physics is math, and we'd all stare at him, and he'd go, blah, 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 and he'd go, and it's obvious that, and he'd go on to the next step, and we'd all sit there and go, whatever you just did was not obvious. We have no idea why you just did what you did. But that he'd always be like, and it's obvious that, and we'd go, no, it's not obvious to us. And so I know that the way that doing a problem this way, it kind of feels that way. So, to walk our way through this, what we're doing is we want to make sure, with integrals, you got to get the algebra down first. And then the rules work. And you got to figure out, like, oh, which one does this look the most like, and figure out how to do the algebra to make it look like that thing. And so, one of the biggest differences between what we had last time and this time is before we had all these ones right here. But now we've got A's. In other words, what happens if we have a number that's not 1? And so what we do is, if you're taking... I'm not going to do the full proof for you, but just algebraically, if you have a squared minus u squared, let's say, that would be the same thing if you were to... let's see. Yeah, let's prove it that way. If we were to say that we had a squared times a squared divided by a squared, multiply both spots by 1, I don't really want to do it that way. That's going to be... Ultimately, I'm not going to worry about the best proof, but the idea is we're taking that a squared and dividing it on both sides. And our rule when we work it backwards is this. And I'm sorry I don't have the official proof worked out for this one, but if you'd like, I can do a proof for you later. But we're using this idea of, if we want it to look like 1 minus stuff squared, ultimately we get this u over a in our relationship. And that's where this is coming from over and over and over again. And ultimately on these ones, we're going to have to take the rule that looks the most like what we're doing, play with it algebraically until we get it to look exactly like one of these rules, and then we can apply the rule. So on the first one, it was pretty straightforward. We could see a squared, x squared. We even had squared numbers. It was set up very, very nicely for us. On these next ones, though, all you really see is you have some number plus something with a squared. Every number is the square of another number. It just isn't always going to be a clean-cut number like you're used to. Sometimes it's going to be an irrational number. And that will pop up certainly in this lesson. On this one down here, I think that on C, the part that maybe felt the most confusing was you only have an x right here, but our u was 2x, so therefore x was the same thing as u over 2, so I had to substitute that in. But that still doesn't look exactly like the rule that I'm using, and so I used the idea that if I have 1 over u over 2, I use my fraction rules, and that's why this 2 came on the outside here. And it just so happened, it will not always happen, but it just so happened here that my 1/2 from my u substitution canceled with the half from my, again, from my u substitution. One from the u itself and one from the du. That won't always happen. It just happened to happen here. Okay, how are you feeling? Let's give a few more a try. And I really, let's see, I've got 1, 2, 3, 4 more examples for the day. Okay, give that one a try. Figure out which rule it looks the most like. I will say, just as a reminder, e to the x squared is the same thing as e to the 2x. That will be a trick for you to use. Okay, if you're getting stuck on this one, there is a place where I expect you to have a little bit of difficulty. Look at the screen for the trick on this one. And then once you have the right trick, then the integral comes a little more easily. But getting the right trick is difficult sometimes. Like, absolutely. Even for me, I've been doing calculus a little bit longer than you've been alive. That's the first time I had a calculus class. Even for me, I have to sit and play with it a little bit to find the right trick. Uh-oh. Get it out. Any questions on that one now? And feel free to ask away. We'll definitely be getting some algebra practice in on these problems, as well as just kind of some sight recognition, we'll say. Would you be okay to take him for the rest of class?
I figured.
I can take him the next class. All right. Let's try another one. He's been spitting up, so he might. Okay, so I want you to look at this one for just a moment before you start jumping in, because there's always a trick. Sometimes the trick is just do the problem, but sometimes there's more of a trick to it. If you were to look at this one, I can see two issues here. Keaton. Or did you have something? Okay. I can see if I use the old U substitution, I get out something that has an x on it. That's actually pretty nice for the first piece of this. I don't get the x plus 2, but I get an x, so that old method actually is kind of nice. If I use u equals x, which means my du is just my dx, and my a equals 2, to use the trig rules, that I can see I'm set up for that, but that's not good for the x in the numerator, aka up top. So let's use both. Let's use both rules. Remember, you can always split a numerator. You can never split a denominator. So it is absolutely a legal move to do this. But don't do what I just did. Remember to put your dx on each of them and give them each their own integral. He just ate at 9. Okay, play with those. And I think most of you see, but if you haven't yet, I do have the problem worked out for you to compare what I've got. Make any changes you need to, make any additions you need to. Aurora, are you talking about going from here to here? Because I got a lot on the screen. Okay, so it's because I have the x dx here, and that was equal to my negative 1/2 du. And so that was equal to this. And then I need a placeholder at the top, so that's why I put a 1 here, to make sure I put everything else on the bottom. So ultimately, this piece I replaced with this. And I could have put the du on top instead of the 1. I just chose to put it out and back like we usually do. But really, on top or behind, they're the same thing, just as long as I don't put it at the bottom of the fraction. Does that make sense? Yeah. No, that one, because of all the rearranging and putting stuff, like, it's not, the substitutions don't go back in the exact same place. So it does get confusing because we're used to substituting it in the same place, and I didn't do it there. I rearranged it as I substituted. Okay, you ready for another one? I've only got 2 left, so we're almost done. Keaton's giving me feedback. Andrew's either giving me feedback or scratching his chin. There we go. And he's giving me feedback. Claire's giving me feedback. Satya's, we're up above the screen. All right. Okay. Short lesson, but intensive on the tricks. Occasionally, you will be given problems that look more like this. The problem with this on U substitution should be very obvious. If we use straight up U substitution, our du looks nothing like what we have in the problem. So U substitution in this case is absolutely not going to work. So we have to think about our other rules, and what should catch your attention is just the fact that we have a quadratic. And remember, I've told you before, everything you have ever learned in math shows up in a calculus class. Everything. Geometry, algebra, trig, all of it. So, for example, one thing we learned in your other classes is there are 3 forms to a quadratic equation, and you can switch between the forms. There's standard form, which is what this is written in right now, which is your ax squared plus bx plus c. My mind is blanking. I know there's 3 forms, but I can't think of what the other form is. But the form that we're going to need is your vertex form. Or CPM referred to it, I believe, as your graphing form. That looked like this. In this case, this one I should say not gives, but this one looks the most like u squared plus a squared. Because again, any number by itself is secretly a squared number because you can always take the square root of it. So already I should have in my mind, I'm going to use the arctangent on this one. The one that didn't have the square root involved. Already I should be thinking of that. But I'm going to have to do my algebra to get it in graphing form. And the best way to do that is to complete the square. Do you remember you doing completing the square back in the day? Seems forever ago now, doesn't it? We've taught you a little bit since then. And it's not always the one we use the most frequently. I do respect that. So I'm going to look at this problem. I've got, let me scroll down for a little bit. We'll look at the problem again in a moment. But x squared minus 4x plus 7. Think about it as literally completing the square. Now again, Nalina and Cormac, I know you probably didn't necessarily learn this method, and I respect that. But what we're going to do is we're going to take our x squared, put it in the x squared box. We take our 4x and we split it in half, exactly in half, so that we get a negative 2x and a negative 2x. And this 7 just hangs out. What I'm going to need to do next is I need to have a perfect square. So remember, this is, by definition now, x minus 2 here and x minus 2 here, because x times x gives me x squared. X times negative 2 gives me negative 2x. X times negative 2 gives me negative 2x. And I use my box method to complete it and say, okay, negative 2 times negative 2 gives me a positive 4. And the 7, I just manipulate it as I need to. This tells me that I have x squared minus 4x plus 4 is the same thing as x minus 2 squared. But I need to go from negative 4 to 7, so I can do it like that. If I do it on one side, I got to do it to the other. Cormac and Nalina, out of curiosity, when you learned completing the square, did you use a literal square?
My camera's frozen, but no, I didn't.
Okay. I didn't either when I learned these methods originally. You did, Nalina?
Yeah, I think I learned like 2 ways, but I don't really remember them.
Yeah, and it's one that if you don't use it, you forget it. I know when I learned it, we had to do there was just the algebraic tricks that we knew we had to take the b value, divide it by 2. It looked a little different than this, but that's one thing about the way Ames taught this method is when you talk about it with literally a square, and you literally have to complete the square, because this last box you need to fill in. You only are given the things in the first 3 boxes, but you have to complete it by creating this last box. And then, like I said, you complete it however you want to do this. The way that I learned it, and this is, if you're not Cormac or Nalina, you can shut your ears on this one. I learned that you add the 4 and then you subtract the 4. And then you'd have this plus 7. And it might seem redundant to add and subtract, but the whole idea is you do want it to cancel, and you wanted to have this part to be your perfect square, and then this part to be whatever's on the outside. Okay, so ultimately now, let's go back to the calculus because we're ready for it now. Go ahead and play with that one. I think he has a pacifier in his diaper box in the bassinet. Did you hear me, Dan? Thank you, Andrew. Okay, and we're ready for the last problem. We're going to use a similar trick on the last problem. I do see some people look like they're still writing stuff down, so I'm not going to start it yet. I don't want to scroll the screen while you're still writing. Although, Annie, I think your screen just froze. Nope, there you are. Okay. All right, we ready for the next one? The last one of the day? Every time I promise you we're getting out early, we don't, so I didn't want to promise it today. Okay. This would be a really good example of, again, it's not obvious that we want to use an inverse trig function rule here. Oh, I almost forgot the dx again. But anything that's a quadratic we can complete the square on, even when we have a negative x squared. And if we can, it's going to take some algebraic manipulation. And believe you me, you're going to want to practice with these things before the AP test because you're not going to know necessarily which rule off the bat you want to use. But the more you practice with these rules, the more you'll get to recognize them. For your test, definitely I would have kind of a cheat sheet next to you. I'd have your book open and just be able to reference them during this test. But of course, the AP test itself, you won't be able to have that. On a problem like this, I know that I'm going to want to play with 3 minus x squared for a minute. And I know that this is going to be the same thing as the negative of x squared minus 3x. And so maybe let's play with that instead, because that's just a little bit easier to handle with the box method. So, on the box method, I know that I have my x squared box. And then the rule says I take the b term, the one with just the x, and I divide it exactly in half. So I'm going to have fractions on this problem. Just realistically, the higher you go in math, the more often you're going to use fractions. And I am going to keep it in fraction form. You could use the decimal here, but I'm going to leave it in fraction form. And by definition, when we complete the square, we know that we have on the outside here now x minus 3 halves and x minus 3 halves are what give us the square we have so far. And so we use those minus 3 halves to come up with what goes in the last box here. And that's going to be a positive 9 quarters. And so, to complete the square, what we're going to do is we're going to say plus 9 quarters. But remember, when I distribute this negative, what I really have is minus x squared plus 3x minus 9 fourths. And so what I really did was I added in a negative. And so to compensate for that, I'm going to also add in this here, because ultimately these two do need to cancel out so that I still have not changed the problem. It just changed how it looked. I don't want to actually change the value. So this one's using the same rules as last time. We made it slightly more complicated because we had a negative in front of the x squared and because we're using fractions. But other than that, it's the same problem as last time. So we can rewrite this as a negative x minus 3 halves squared plus 9/4. We've gone from standard form to vertex form. And to put it in the form I'm more used to, I am going to switch the order so that I have the minus in the middle instead of in the front. It just makes it look more like what I'm looking for in my problems. And now I'm ready to start thinking calculus. And then these last steps are just about me cleaning it up, just because the fractions over fractions gets messy. And there's a couple different ways you can make your final answer look. This is just how I chose. Was I used my fraction rules. And while it might not feel like it, I did use the rule about flipping that last one upside down, or the bottom one upside down. So I definitely did include these on your test, because it is a chapter 5 test. There is one section, if you have your book, you might notice we do have one section we've not covered yet, and that's hyperbolic trig functions, which is about the only thing in your textbook that we have not done in a previous class. I don't believe any of you have learned hyperbolic trig functions. And to tell you the honest truth, they're not going to be that big a part in the AP test. So if the AP test is going to be the 1st of May, it's something I'm just going to skip over. If I find out we're not going to have you do it until the end of May, I still might skip it because it's not going to be that huge a deal on the AP test. And what's coming up in the chapter 6 and 7, because I do still have 2 chapters I have to get through. What's coming up in those chapters is going to play a big part on the AP test. So I'm not so worried about the hyperbolic trig functions. It's just another rule that if it looks like this, you use this function. But we haven't ever taught you what a hyperbolic trig function is, so people do get a little twisted on that. I will, like I said, I'm going to email the counselors and Mr. Katoa today and find out what the plan is for the AP test, because that's going to determine how I'm going to teach, or what I'm going to teach for the rest of the year, what schedule we're going to try to keep. You have 2 weeks to do this test. If you wait until the end of the 2 weeks, it will be very painful. I think I put 24 questions on the test, I want to say. And a lot of them are using these new rules, and some of them just won't feel that straightforward. And if it's not something you can do in an hour necessarily. But at the same time, I didn't make it to try to take you the whole spring break either. But not by any means. I want you to have a spring break. Mostly I'm taking advantage of the fact that we don't have class Wednesday and Thursday, which normally we would. So I would please try to get it done this week. If you have other plans that have come up for Wednesday and Thursday, especially, and Friday, just send me an email. I'll work something out with you. But aim on getting this done before the official spring break starts. Okay? So that you can give yourself plenty of time just to play and relax and do this. But because of the schedule, I didn't feel right about trying to come back and do this test after we came back, because that would take a whole week of class periods, because we'd have one for a practice test and one for the regular test, and I don't have time to give those days up. I've only got like 8 class periods with you left to do 2 chapters before the AP test if it's that early date. So I decided to do this instead for our schedule. You guys already have your study groups. You can also reach out to other study groups. This is open book, open note, open partner, whatever you want. There's the Discord group that's going on. If you need access to that, just let me know and I'll get an invite from Cormac to send to you. Do you have any questions for the day? Okay. Ultimately, today you watched me do examples of what these are going to look like. Your goal now is to play with your own problems, and practice with those. So, give me just a second.